So let us talk about morphological image algorithms. We will see this boundary extraction, hit and miss transform, region filling and skeletonization. Also we'll talk about this grayscale morphology. So boundary extraction, this is how we find the boundary. So to find this boundary of set A, this is set A, we want to find the boundary of set A. What we do is we erode this set A by small structuring element B. We take a small structuring element, erode this A by this structuring element B, and then we take that set difference between this A and this eroded result. So A minus this eroded result will give us the boundary. This is the boundary. So this is an example. This is a simple binary image which once represented in white, and this is the result of using this expression with structuring element. So this is how boundary extraction is done. Now we come to this hit or miss transform. So what we do here, this is a method to find a location of shape B1 in an image A. Now the erosion of A and B will give us all the places where this B1 is going to fit in A. But B1 fits in any sufficiently large shape. Any sufficiently large shape B1 is going to fit. So this will give us a false alarm also. So what we are going to do, we are going to erode this A complement with B2. We require the boundary around the shape B2 to be empty, and we erode A complement with this B2, and which gives all the places where B2 fits in empty places of A. Then we take the intersection, means A, this dilation B1 intersection A complement dilation B2, and the following result will actually give us the hit or a miss. So it will give us that this shape is available or not. So if you are not getting this particular thing, I'll show you with an example. This will help you more. Now consider this is set A, which comprises of this X, Y and Z. Now if I use this X and I want to find out the dilation A with this X is the shape we are interested in. So if I find the dilation, this will give this result. Okay, this is the dilation result. Erosion result. This is the erosion result. Now what we do is this fits here, no problem. If we erode it, we'll get a point, and this X is going to be fitted here, no problem. But what about this area? This will fit here also. X will fit here also. So we have to do something for that. So we'll take W and we subtract this X from W, and we get some result like this, and keeping this shape alive of X. Now we take a complement of A. This is A, we take a complement of A. And now what we do, we erode this A complement with our W minus X. So what it will give is, it will clear off all those other things, but this will find its place here and somewhere here also. But when I intersect this and this, when I take an intersection, we'll only get this and this as the proper position. This all will be gone. So this is how our false alarm will be goner, and these two proper shape or this fitting can be seen. So we say that this is a perfect hit. So now let us come to this region filling. What region filling does? Now this is our area, right? This is our area, and I want to fill these areas. I want to fill this particular region. So how we are going to do? Let A be the set of 8 connected boundary points of a region. Let A be like this, and we start with a position or point inside the region. We start with a point. See, this is the point which is inside it. Okay, and we take the complement of A. This is A. We take a complement of A. This is set A. This is complement of A, and this C, this particular is the structuring element of B. This is a structuring element. This is the initial point inside the boundary we have to start. And these are from this to this, what is happening? These are the various steps. And what are the various steps? What we are using is we repeatedly dilate. We repeatedly dilate this value. And when we repeatedly dilate, at each step set to 0 the points corresponding to the region boundary. So what we do is, whenever we are dilating, we are doing this x k minus 1 dilation of B, intersection of A complement. So we are ensuring that we don't go out of the boundary. This ensures this. This is how region filling is achieved. This is skeletonization. We have to see this is the set of all points that are equally distant from two closest points of the object boundary. Equivalently, this is the union of all maximal disk. If you consider this to be disk, all maximal disk centers that are contained in the object. So you just roll on this disk in this particular figure or here, right? So the locus or the point it makes, or the line it makes, the trajectory it makes, is the concise representation of the shape. So we can make an analogy: start a fire at the boundary and let it burn inwards. So points where the fire is quenched are the skeleton. This is an example of Matlab. You can use BW morph and you can find out the skeleton. This is ABC, this is an image, and this is the skeleton image. But results are sensitive to these small perturbations in the boundary. If some nature is there, see, a problem will come here, and this we don't really want this to happen. Now coming to grayscale morphology. So instead of binary image, assume we have this gray values of xy, where xy are integer pixels. Let this xy with the gray level structuring element, and bxy intensity profile. These are the this is the non-flat flat SE, and this is flat SE structuring element. So we will try to focus on this flat or constant value structuring element. This. So this is a image, and if you want to see the profile, it is like this. Okay. So how to do this grayscale morphology? The definition of dilation with flat structuring element is like this. This is the dilation, because dilation and this erosion will do on this grayscale. So what it does is, it finds the maximum of x minus f, x minus s, and y minus t. So this reflects BST, slide it past fxy at each position, take the maximum of fxy within the window of BST. So I'll show you how. This is our BST. What we do, we slide it through this line. Okay, till the time it touches. It comes here and it touches. So we take this point. Again we slide it like this. This is our SE. We slide it and this will come somewhere here and this will touch. So we'll just slide it till the time it touches this actual graph. So we make a graph of these points, the maximum. This is the maximum of this. So we get a dilation here. So in this way, it is found in this way. While in this grayscale erosion, what we do for flat SE, the erosion is done by this sign. This is given by minimum of fx plus s and y plus t. So we slide this BST past fxy at its position and take the minimum of fxy within that window. How it is done? This is how it is done. So what we did, we took our SE element here and then slide it from the below, and from below it came here till the point it touches the actual graph, and we make the locus of these points. This is how the minimum grayscale erosion width takes place. This is an example. This is a grayscale X-ray image of size 48 and 425 pixel. This is erosion using a flat disk SE with a radius of 2 pixel, and this is the dilation using the same SE. Now opening and closing, this is similar to the binary case, and opening is erosion followed by dilation, and closing is the dilation followed by the erosion. So this is the geometric interpretation of opening. What we do, we push the SE up from the below against the underside of F and take the highest values achieved at this point. Previously we took the lowest point, we will take the highest point. And this opening removes all the bright details. While in this closing, what we do, we push the SE down from above against the top of F, and we take the lowest value which is achieved at every point. So closing removes small dark details. Now coming to this top hat transform. What we do in this top hat transform, we do something like this. We take an image and subtract F of this B. So open the image with the structuring element, subtract it from the original. So it leaves only details smaller than the structuring element, right? What we do, we open the element or open the image with the structuring element. That is what we have seen opening just now, and then subtract it from F. So what we get is, this was the actual figure, if we understand, and we find out this opening. So we get this dot green one, and when we subtract, we get only these hats. These are the top hat transform. This is the example of a famous rice image. And what we do is, we take a structuring element, we just find out the background and subtract it from I. This gives us the proper top hat transform result. Now morphological operations are useful set of tools for extracting features of interest in a binary image, which includes finding connected regions, filtering out very large or very small regions, and finding the boundary of regions, also filling in the interior of regions, and finding the skeleton of a region. And this morphological algorithm can be extended to grayscale images also. So hope you got the idea. Thank you so much. Take care.